Good morning. Thank you, Ronnie, for the introduction. Thanks to the organizers for inviting me to this event. I'm very excited to be here. And today I'm going to talk about, roughly speaking, autonomous online navigation, online perception. And specifically, we are going to provide some overview of some of the works that we did in the last few years in the group. As an introduction, let us recall what does it take to do autonomous navigation perception with a focus on unknown or uncertain environments. Well, basically, we require to do SLAM, basically, which can be broken down into perception and inference, asking questions such as, where is the camera located? What is the environment that the camera observes as it moves in the environment? And this question, what is the surrounding environment, can be referred to only geometric aspects, such as 3D construction, as shown here, but it could also refer to the content of the environment, so meaning more towards the classification or semantic aspects. What is it that we observe here, and not only what is the 3D location of that object or that scene. And on top of that capability, we are actually required to ask the following question: what should we be doing next as the autonomous robot, vehicle, quad, whatever? Right? So in this work, in this talk actually, we are going to ask actually this second question: what are the next actions? And to answer this question, we are going to frame the problem within the framework of beliefs planning, or planning under uncertainty. Roughly speaking, we are required to determine the best actions or suboptimal actions while accounting for different sources of uncertainty that we have in the system that we know at the current time k, planning time. And apparently there's a tight coupling between perception and inference, for example, visual SLAM, and planning or active perception. And there are numerous problems in robotics and autonomous systems that are related or could be framed using such a paradigm. Some of these problems are written here, so autonomous navigation, active SLAM, informative sensing, informative planning, sensor deployment, and many more problems. And let us briefly introduce what we mean here. There will be not much math in this presentation, but still let us be a bit more concrete. So let us assume that at the time k, the current time, we have some state, x, a high-dimensional state. And let us assume we have some models, probabilistic models for how the state develops over time. This is the transition model. And we have a model, probabilistic model for the sensors that we have in our hands, for example, a camera, laser sensor, and so on. And at time k, we are able to speak about the belief, which means the posterior distribution, probability distribution function over the state, given all the data that we have so far, meaning actions that we performed until the current time, and observations that we receive from our sensors. We will refer to this guy as the history time k. This is the history that we have. And for example, in the context of SLAM, we can imagine the camera moves in the environment, so the state, let's say in the full SLAM paradigm, the state might be all the camera poses until the current time, plus the landmarks, the 3D points that it reconstructed, if it is full SLAM, if it is post-SLAM, then without the landmarks. Okay? And so all these things could be represented also using graphical models. It's a known thing in SLAM community that is exploiting sparsity of the problem. We can represent the problem using graphical models. So this is an illustration of just a representation of the underlying factorization of this belief. Okay, so you can see here the camera poses and landmarks, and each edge here corresponds to an observation of, let's say, the jth landmark from the ith camera, and so on. Okay? All right. So this was the passive problem, meaning this is what we have the current time k. Now, if I move towards the autonomous part, so I would like to make autonomously decisions about the next actions. So we are required to to solve the following problem. We have a user-defined cost or reward function over the belief at the future time, and we are required to find the best action that minimizes the expected cumulative return or cumulative reward, right? And the expectation basically accounts for the future observations that I might get in the future as a result of performing some action. So you can see here inside, in the belief here, the belief is conditioned on the history, the current time, but also on the future actions and the future observations. Since we do not have access to the future observations, we are trying to account for all the possible values these observations might assume. Okay? Of course, solving this problem exactly is intractable computationally. It is actually a variation of a partially observable Markov decision problem. So our focus in this talk will be on approaches that are aiming to calculate these things approximately online while accounting for different sources of uncertainty and ambiguity. And in particular, we would like to operate reliably in scenarios where the environment is uncertain and perhaps also aliased, so different objects that look alike, for example. And to put this in the context, let us show you some movie. There will be not many movies in this presentation, sorry about that, but still let us just show some movie that we recently made in our lab that basically shows a multi-robot collaborative setting where there are two quads here. Each one has its own goal. They are planning their actions according to some uncertainty criteria. So let's say minimize the uncertainty towards the end of the scenario. And on the way, they map the environment using, in this case, PostSlam. So we are basically reconstructing the environment, the map of the environment in terms of occupancy grid. And the quadrators basically collaborate with each other, and via this collaboration, they are able to reduce the estimation uncertainty in an active manner, meaning they identify the best actions that will lead us to the minimum uncertainty possible under this setting. So this is, so you can see here in gray candidate actions, and for each candidate action, we are required to evaluate the objective function while accounting for future observations that we might get. And this is just a visualization in MATLAB. Afterwards, we can see the uncertainty ellipses here, the covariances of the two quads. And the red parts here basically denote the collaboration aspect, meaning two quadrators observe the same scene, not necessarily at the same time. So we use these aspects to reduce uncertainty even more. Okay, so this is our context. And to do these kind of things that I just showed you, we need to solve these. And in this presentation, we are going to provide an overview of some of the recent approaches that we're developing in the group that, again, aiming to address belief explaining in high-dimensional state spaces. And the first one will be an overview of an approach, of a recent approach developed by Elad, a PhD student in the group, that basically calls for incremental belief explaining, meaning reusing calculations from different planning sessions. And this is in contrast to the current state of the art that basically, while replanning, basically replan from scratch each time. So you can imagine that we are now at time k. We have access to the current SLAM solution or to current belief, and we look L steps into the future. So we are now here, we look L steps into the future. And we are trying to solve, to find action, the best trajectory perhaps, such that this thing is minimized or maximized, depends if it's reward or cost. Let's assume that we solved that and we executed part of the action. And now at the next time, let's say k plus L, we are required to solve again the same system, but now the information that we have has been updated because we mapped new things, the environment might have changed dynamically over time and so on. So we need to solve the decision-making problem once again, And the question is, can we utilize the calculation that we made in the previous planning session such that the current planning session can be solved more efficiently, online, hopefully in real time. So roughly speaking, if you open up this expectation and approximate it via sampling, you are looking into this decision tree. So where this is, let's say, planning session time k, this is the belief, and we consider all the possible actions, and for each action we consider all the possible measurements and so on down to the decision tree. So this is a decision tree of L look-ahead steps. It's intractable to calculate. But let's assume that we calculate it somehow. Now we are at time 2, and the idea is that if we identify that this is the best action, this branch in the tree, and we executed a portion of it, let's say we executed just this first action, the idea is to reuse information from this subtree, sub-branch. And the question is, how can we reuse it reliably and efficiently? Okay, so I will not go into much details here, mathematically, of course, but the idea is that the two planning sessions differ mainly in the new information that we got from the perception inference between the two time instances, k and k plus L. And as a result of that, they will also differ in the sample measurements because the measurements are sampled from different distributions. And so roughly the idea is to resort to imported sampling techniques to update and to selectively resample the measurements from the previous planning sessions. And again, if you're interested, there's a paper. But the bottom line that these kind of approaches result in substantial reduction in computation time. For example, it can be by a factor of 10 or 5, while the statistical accuracy is not damaged. So here's just basic simulation, more results in the paper. So here's a simulation of navigation to some goals. We start with some initial belief. It's a very basic simulation just to clarify the concept. And we have two goals, goal 1, goal 2. And we compare here between maximum likelihood belief system planning and incremental maximum likelihood. ML here refers to just one sample, one observation, one sample measurement in the future. And you can see here that statistically, the estimation error and the covariance at the goal is roughly the same, but the compute time is drastically different with this incremental probability. Okay? So we are very excited about this approach, and now we are looking into how to extend it further. So more results will be out soon. The second topic that I want to highlight here is a new paradigm that we believe that is of interest to the community. And this paradigm calls for addressing the decision-making problem via approximation or via simplification. So I will provide an overview of this concept. This is work by Han, also a PhD student in the group. And here's the idea. So we'd like to find some simplified definition of the problem, some simplification of the decision-making problem, such that, and solve that problem in a simplified manner, such that the solution will be as close to the optimal as possible. And this idea is based basically on the following key observation. Basically, what we care about in decision-making is what is the best action. We don't care about the value, typically, of the objective function, just the best action. So as long as we are able to preserve the action sorting between the different planning problems, we are good, we are fine. So basically, we would like to find, so you can see it here basically, x-axis corresponds to different actions, y-axis corresponds to two different planning problems or two different presentations. Let's say blue one is the original unapproximated problem. Green one is the approximated problem. So you can see the values on the y-axis are different, blue and white colors. But as long as the two curves are aligned on each other, or as long as the trend of the actions is the same best action will be chosen. right? So we don't hurt the decision-making problem at all. So the question is, can we actually find some simplification that will guarantee such a concept, that will guarantee that, you know, the decision-making problem will not be, damaged? And if it is sacrificed a bit, what is the sacrifice? So we call this concept action consistency, where for any two actions here, if the original objective function, for two actions, if there is some relation, let's say action A is better than action A prime, then necessarily the same relation will hold also to the simplified problem. If we can find such a simplification, we call such a simplification as action consistent. Why? Because again, we will get exactly the same optimal action in this case. Of course, in practice, it is difficult. So in practice, many times we cannot guarantee action consistency, and there will be some, sacrifice in performance, and we can measure this sacrifice in performance by inducing this error or loss between the original objective evaluated at the optimal action versus the same value evaluated at the optimal action of the simplified problem. And ideally, we would like to find bounds on this loss. This is a framework. And now I will try to provide you two perspectives that we have been investigated within this framework. And for this specific case, we are considering the following setting. We consider high-dimensional Gaussian beliefs. For example, it could be a SLAM problem. So we map the environment, and we have the trajectory, and the belief is over the trajectory and the map. So it's a high-dimensional setting. We consider an information theoretic cost, let's say a reduced uncertainty of some variable or of the entire system. And we consider ML observations, meaning we drop the expectation. We consider only the most likely observations, just one sample. And now we'll go over two perspectives that we have been investigating in the group. The first one is by Andrei, who is a research scientist in the group. And this one is called topological beliefs explaining. And the idea is the following. Let's look at the graphical model that corresponds to a given belief. The idea is that we want to design some cost function, another cost function or metric that will be highly correlated with the original information theoretic cost, entropy, for example, and will be highly correct and will be very efficiently calculated. Okay? And this idea is based on some progress that has been made recently in the community that basically says that topological properties of factor graphs, just where are the connections, they are the de facto or very important and basically indicate the estimation accuracy. Meaning, if I just look at the edges of the factors, where are the edges and where there are no edges, I can roughly say what is the estimation accuracy compared to some other factor graph. Okay? And so Andrei has been working very hard to design and develop a new metric in the topological space, which is only a function of the topology of the graph. And what he came up with is this metric. It's an approximation of the so-called phenomenon entropy. And as you can see here, it is only a function of node degrees, meaning how many edges are there at each node. Very easy to calculate. And here you can see on the x-axis information theoretic cost, entropy. Y-axis is this signature. And you can see here very high correlation. Each point here corresponds to a different factor graph, different topology. So meaning that I can solve the simplified problem, in this case using the topological metric, and still get the same solution. And the nice thing here is that this signature can be very efficiently updated incrementally, such that in practice calculations are nearly O of 1, really constant time in high-dimensional setting, loop closures and so on. And additionally, as you'll see in the paper if you are interested, we have bounds on these things, meaning we can whenever action consistency is not guaranteed, we can say how much we might sacrifice here. So here are some results. These are results in the gazebo simulator. So we have some map, some building, and we are using, in this case, a probabilistic roadmap to sample the environment and generate candidate actions. And we have here 2 planning sessions, each one to a different goal. And here you can see for each planning session, again, the comparison between entropy and the topological cost. You can see that roughly there is very strong correlation. And in terms of time, compute time, you can see that the metric, the topological metric is by far much more efficient. It's really very, very efficiently calculated. Here's an experiment that was performed in the lab recently. So we have a Pioneer robot. So let me go back. So we have a Pioneer robot here that operates in a closed room, and we project on the floor the memory or the belief the Pioneer has about the environment. So you can see here the candidate actions on top of a PRM, on top of a probabilistic roadmap, and at each planning session, the Pioneer robot needs to decide the next action autonomously, drive to the next goal, and the process repeats. And you can see here different topological graphs for different candidate actions. And you will see here also the comparison between the topological and the metric cost. I will skip a bit these things just not to bore you. And eventually the robot decides on the best action, executes the path. You can see here that while it executes, it maps the environment. So we know exactly from the SLAM system where the robot is. In this case, the robot uses laser data, in this case, within post-SLAM framework. And until it reaches the next goal, and then it begins to plan again to the next goal. So we'll see it in a second. So it will reach the goal roughly here. And now he plans again. So consider different candidate actions. For each action, the corresponding topological factor graph topological cost. And then it chooses the best action according to minimum uncertainty via topological signature that I just said. Minimal cost in terms of runtime. And then it executes again the action. And let's say this is the trajectory that it's chosen. And so it will now execute the trajectory while mapping the environment and updating the belief accordingly. All right, so I think you get the concept. So that was the topological perspective of the simplification. And now I'm going to present briefly, really, another perspective that calls for another sort of simplification, this time via sparsification of the belief. How much time? 3 minutes. Good. So in this case, the idea is the following. Let us look at the information matrix of the Hessian of the system. It's a high-dimensional setting, so matrices are huge. And the question is, can we sparsify some of these matrices, some of the elements in these matrices somehow? And the question is how, of course. Can we sparsify the matrices such that calculating the information theory cost, entropy, for example, will be action consistent, meaning the same trend? And if not, what will be the loss? So I will skip the details, of course, but you can see here again in a gazebo simulation, a very realistic simulation, we consider different sparsification levels, let's say sparsifying only some of the variables or sparsifying the entire matrix accordingly, modifying the diagonal. It's not the same diagonal here and here. And you can see here, runtime for this guy is many, many factors slower than the original problem, while the action consistency in this case is guaranteed. Okay? So I have only 2 minutes left, so let me just briefly overview another big thing that we are doing in the lab, and this is how to cope with ambiguity in the environment. What happens if objects appear similar in the environment, so perception aliasing. So this work was published in IGRR, basically integrates within planning, within belief system planning, reasoning about ambiguous data association while accounting for uncertainty localization. And roughly speaking, if you look at the Ullman building here at the Technion, this is the second floor, this is the third floor. Images look very similar to each other. I might mistakenly think that I'm in another floor, so I must basically maintain hypothesis here. And so the approach basically maintains hypotheses about data association and within planning, within the future, and reasons about how to disambiguate those hypotheses for different candidate actions. And I will skip the details, of course. Let me skip this. And finally, recently, we have been investigating similar things also into semantic SLAM or classification aspects. What happens is that if the object appears similar to different classes, so classification is ambiguous, what should we be doing actively to disambiguate classification labels and so on? So to summarize, we presented here a brief overview of what we've been doing in recent years in the context of belief system planning in high-dimensional state spaces. And here are the students, research scientists, and postdocs that are responsible for this research. Thanks a lot.